Greetings and welcome to Unveiling a Titan, Part 4, where we'll be taking a close look at the histology or tissues of the mountain Mont Go. If you haven't already seen Parts 1 through 3, I highly recommend that you go back and watch those first, as you'll get a lot more out of this video if you're already familiar with the topic. If you have seen them, you probably noticed that the introduction was a bit longer this time. That was the original intro that I created for this video series, but after showing it to my friend Alex, he thought it was a bit long and there were a few parts in there that didn't quite make sense to him. So we shortened it down to 30 seconds and made it a lot more gripping. And I'd like to thank him for that and so much more. Alex, conspiracy music guru, you are epic. So the reason for the longer intro this time is because it's a nice condensed summary of the first few videos that I did, and it also includes a bit of foreshadowing for the things that we'll be covering in this video. And if you've seen the first few videos, you'll understand that there's already a great number of coincidences that have been stacking up with regards to this mountain and that it may actually be a Titan elephant. In one of the comment threads of one of the videos, somebody asked me the question of how I thought Mont Go may have met its demise. My first thought was drowning, and this picture would be a good idea of what that would entail. Some grand mud flood that swept over the earth. That would explain also the fossilization process. But then as I thought a little more about the question, it occurred to me that maybe that was an explanation for the fossilization, but not for the death, that maybe Mont Go died in a more sinister fashion. So I'm thinking perhaps it was a murder. Maybe there were elephant poachers of a gigantic scale and they bludgeoned the poor beast. So if we look here, mainstream geology, as I mentioned in the first video, talks about this curvature here. It's known as a synclinal. It represents a collapse of this section of the mountain. I'm thinking perhaps Mont Go actually died of some kind of a giant head wound, and the blood and brains and whatnot oozed out the sides, and that's why the mountain looks the way it does. So I decided to approach this whole thing from the perspective of a crime scene. And a prosecuting attorney, if they're going to get a conviction, they need the help of forensic scientists who go in and analyze all of the different evidence that's found at the crime scene. So that's what we're going to be doing today. So this is what I was describing before, the synclinal. This is an actual page from a geological survey of the mountain. And the way I see it is that this whole section here where the breathing passage is may have collapsed, and then you would have all of that runoff going down to the sides. These are some examples of what these synclinals look like. It's the result of compression that occurs during orogenic events. And I didn't know what that was, so I looked it up. And it's the process of mountain formation, especially by folding and faulting of the Earth's crust. So essentially what we're looking at here is Mont Go's erogenous zone. Sorry, I couldn't resist. If the prosecuting attorney is going to get a conviction, they're going to have to live up to the burden of proof, and they have to convince the judge and jury that the defendant's guilt is so sure that there's no way a rational person could have any doubt. So if you were to think of it as the court of law, the question is how many coincidences have to stack up before you get a conviction? If this were the O.J. Simpson trial, I would say that the prosecution would already have a slam dunk as far as conviction goes. This is the list I've already shown a couple of times of coincidences. Some are very, very specific, and the areas in blue are what we'll be covering today. So obviously the gold standard when it comes to crime trials is the DNA blood test, and at some point I would love to take some samples from different rocks around the mountain and send them into a laboratory. I'm hoping to maybe set up some kind of a crowdfunding campaign to make something like that possible. I've heard that it's challenging to find reputable laboratories that will touch these kinds of tests now. Might have something to do with what Roger from Mud Fossils University has already done 3 different DNA tests, and apparently all 3 have come back conclusive for humanoid DNA. You can go to his website, click on the PDF, and download the report. Unfortunately, even with 3 conclusive DNA tests under his belt, Rogers' work has been ignored by mainstream academia, and I think it's quite simple, really. The fact of the matter is that if what he's saying is true, it's a paradigm-shattering revelation, and everything that we know about geology and the layers of strata and the timeline of when things happened, all of that has to be revisited and revamped because it's based on erroneous thinking. Combined with all of the other evidence that I've gathered, the DNA test would really be the final nail in the coffin in concluding that this mountain was actually once a giant creature. Unfortunately, since we don't have that yet, we'll have to rely on a forensic analysis. And as I've mentioned before, the primary tool of a forensic scientist is the microscope, and when you're dealing with something the size of a mountain, you are the microscope. So I just want to review a little bit something that we covered in the last video because it's very important for all of the things that I'll be covering today. This is looking at a cross-section of the skull bone, and you can see that it looks like a sandwich. You have 2 thick layers of solid bone, and then this is known as spongeous bone. And as I mentioned before, this is where the blood is formed in both the skull, but primarily in the long bones of the body. I talked briefly about this as well. This area here, I'm theorizing that this is the spongeous bone that's been exposed. So the outer layer has fallen off, and whenever you're walking around the mountain and you see a chunk of stone that has fallen away from the mountain, then it exposes this reddish, iron-rich area. And you can see this here in a very large segment that's missing. All of the horizontal surfaces of the mountain are covered in what is known as karst, which is another form of limestone that's notable because it has all sorts of different channels and fissures in it, which mainstream geology tells us are formed because of the acidic nature of rain mixing with the limestone and dissolving the calcium carbonate. So these fissures here, they grow as time goes on. That's according to the mainstream model. I would suggest that there's a simpler explanation, that these are actually channels that are formed by blood vessels. And as we go through some of the samples that I'll be showing later, I want you to keep this mainstream geological explanation in mind because I don't think it explains a number of the samples that I'll be showing you today. So this is just showing how limestone water with weak acid solutions will erode the limestone and lead to karst landscapes. So we're going to be looking at a lot of different rocks today, but essentially they're all part of what I think is just 2 different kinds of bone. If we look at the long bones, we've got this compact bone area here, which you can see better here, which is in layers, and I'll show another picture in a moment that illustrates that from a different angle. But inside is the spongeous bone, filled with all kinds of blood vessels. This is where the blood is produced, the red blood cells of the body. Your bone marrow is there, big portion of your immune system as well. This is looking at the cross-section of the compact bone. It looks like layers of a tree growing outward. And if we're talking about something the size of the mountain, then each one of these little lines would be, in the case of Montgó, something that's about 3-4 feet thick. So this is trabecular bone. If we look here, this is looking at it under a microscope, and you can see it's fractal in nature. You've got bigger and bigger holes going down to smaller and smaller and smaller holes. This is a pelvic bone, and you can see here when the outer layer is broken away, you get the spongeous bone exposed. And here you can see more clearly, all of the blood is gone from this particular image, and you can sort of make out the lines of the compact bone. You have lines going this way, but also lengthwise. And here it is with blood. And cross-section with the blood remaining, but all of the water is gone, obviously. So keep this image in mind when I start to show you some of these rocks in a moment. Most of the specimens that I'll be showing you today are going to be from this region of the plateau. And we talked before, I'll mention it again in a little bit, but this area here, this is what all of the Earth looks like when you scratch at the surface. Any rock that you lift up, you got this reddish colored earth. Mainstream geology would be telling you that these channels are formed by water moving through and slowly eroding and creating larger and larger fissures. So all across the plateau are rocks that look like this. They're either filled with reddish earth or the earth is completely gone and you just have a nice channel there. This is also found all over the plateau. This is iron ore, and you can see here it's stuck to the sides of the rock, and all of these rocks are just filled with iron ore on the outside or in these channels, and it clumps up. Now I theorize that this is arterial blood flow. The arteries contain iron-rich oxygenated blood, and this is iron ore. So if we look at the artery vein system, the arteries have higher blood pressure and there is no obstruction, whereas the veins have a lower blood pressure and they have these little valves that open and close as we walk, for example, and our muscles contract, and they actually help to pump the lower blood pressure blood back to the heart. And the oxygenation, if you look here, this is the heart. It's pumping the blood that's filled with iron and oxygen out to the body, and then the oxygen is used by the cells, and then it's pumped back up into the lungs and then down back into the heart where it's pumped back out to the body. Hemoglobin is the part of the blood that the oxygen binds to, and that's got iron in it. If we look at the constitution of blood, you've got the red blood cells making up 45%, and then plasma, which we'll talk about a little bit later. So this is iron ore, and iron ore is found all over the plana. And you can see here the rich red color of the earth below. And the iron ore is very often stuck to the side. I've theorized that it's coagulated blood, that it seeps out of the broken tissue and then it starts to coagulate and harden. Here you can see a specimen up close. I think that all these little cracks and everything, to me this looks very biological. Doesn't look like something that was formed by chance. You've got all these different passages going different directions. And you can see how this iron loves to stick to the sides of the limestone. And then inevitably there are these channels that are filled with combinations of red earth and chunks of this little iron ore. Now again, ask yourself if these look like fissures that are formed from water going through cracks, or if this looks more biological in nature. This is one of the fields that I showed before from above, right here. You can see the trees and the rich red color of the soil. And again, you can see here that everywhere there's a channel, there's reddish blood. Now, obviously, a flood could come, cover this rock, and then those channels would fill with the red blood. But I'll be showing some samples later on of rocks that are broken open and actually exposing channels inside that are also filled with mud. And I have a hard time imagining that the mud would be able to work its way in. And to me, this looks incredibly like trabecular bone. This is sculpture from, can't remember the name of the lake. They like to make artwork out of the stone. So here we see this tree-like nature of the osteoblasts that create this circular bone. And then you've got these long, straight, parallel layers. So if you were to imagine the bone being crushed, then that would expose the trabecular bone in the middle, but it would also, on the sides where you see the break, it would expose these different layers in the bone. So again, take a look at this trabecular bone and compare that to this. This is rock that's found on the top of the mountain. And if you think about the skull, the top layer of the sandwich being eroded, then that would expose this. So we'll come back to the compact bone in a moment, and I'll show you lots of examples of different layers of compact bone on the mountain. But first, let's just look once more at the trabecular bone and compare that to this. This is found on the top of the mountain. So if we think of the top layer of the sandwich having been eroded as a result of rain and erosion and wind, and then this section here being exposed, that would be anchored firmly in the bedrock of the bottom layer, and that's exactly what we're seeing here. So if we compare the trabecular bone in the long bones of the body to the trabecular bone that's in the skull, this is of a much smaller nature. And if we look at the rock that's found on the top of the mountain, the skull, and we compare that to the rocks that are found below, you can see these channels are huge compared to the ones that are found on the top of the mountain. So I think that that's fairly consistent with what I would expect to see as far as the erosion and the exposure of the spongious bone of the skull as compared to the trabecular bone that would be found from the long bones on the plana. Here you can see just how small the trabecular bone can get up on top of the mountain. And I showed this picture in the last video, but this is the top of the mountain. This is looking at the cross from the direction of the peak, and all of this karst landscape, which I believe is trabecular or spongious bone, it's all anchored in the bedrock, and that's consistent with the anatomy of the bones. You can see it's just a sea of trabecular bone.
I would hazard a guess that these rocks are essentially the same as the ones that are down on the plana, which are a totally different color, more like this color. But they're filled with all kinds of blood vessels, just like these. The thing is, because we're on the top of the mountain, these have had all kinds of rain and wind and sand erosion, and all of the blood has long since been washed away from the passages in the bone.
So this photo was taken down on the plateau, and this is a perfect example of what I'm talking about. So this would be the bottom layer, the bedrock, which the trabecular bone is fastened into, and then the top layer long since gone. So that would be this with the small attachments on top that are still remaining. This photo is just a reminder of how bone looks when all the blood has been removed. And this is a middle stage in the process. Looks just like the rocks on the plana. So now we're going to take a close look at the compact bone, these layers here. So you have these long layers, and then you have these rings that are formed. And this is a petrified bone. You can see the rings are present. And this is looking at the side of the plateau. And you can see there's this layering. Now, if you notice all this rock here, it's completely lacking in vascularity. There's no blood vessels here, except in, some cases there's small channels, but essentially what you have is piles of 3-foot thick rock that are just layered all the way up to the top. So I believe that the top would have been crushed, and that's why we get all of the trabecular bone, and see more examples of that. So this is very indicative of what you find. It's either going to be the trabecular bone or it's going to be the compact bone. Wish I had a better zoom, but here you can get a sense of just how massive these layers are and how deep they go. You can't really appreciate that when you're looking at some of these other areas, but there's a gouge and some of the layers have fallen off. That's probably, guessing from here, probably 10 to 12 feet deep, that layer of rock. So again, if the bone were crushed, then that would be exposing some of these layers, and I think that's what you just saw in the video. Here's a cross-section of elephant tusk, so you can see the same thing. And here you get a real feel for it. So this would have originally been extended around perhaps, and then this plateau is filled with blood and trabecular bone and little scattered pieces of these thicker layers, but along the side of the mountain you get all of this layering that I'm talking about. Again, noticeably lacking in blood vessels. Here is what I would consider to be like a transition segment. You've got nothing in the way of vascularity, but nevertheless there's iron ore deposited here. So this might have been what I consider a transition zone between the two kinds of bone. Again, here, huge block. Can't really get a sense of the size because I don't have anything for scale, but this is probably 4 feet high. And you can see there are blood vessels here, but they're smaller. So this, I'm thinking, is more of a transition bone. This is nearly the size of a car. And this is a real fascinating specimen because you can see down here, this chunk has broken away, exposing the inside. And you can see here that where that rock is broken away, there's literally red earth oozing out of channels. And this is the size of a car as well. Another angle. Okay, so just to drive the point home about compact bone and what I consider to be transition zones, this is a huge rock that's about the size of a car. There's a plum there just to give you an idea of scale. You can see the blood here that's coagulated, and then down below you'll see in the video there's a, let's just run it. You can see there's a channel just below where an animal has dug out, exposing the red blood. See a massive blood vessel there. That's about I don't know, 10 inches wide. So if that was created by erosion, it's interesting that it's almost a perfect circle and it's so large. And here we're looking down into larger blood vessels, and if you look, each of these larger spaces here break off into smaller channels. So this is exactly what I would expect to find with the fractal nature of blood vessels. There you have it. Compact bone, probably a transition zone because of the huge amount of vascularity. Okay, so let's talk about plasma now. If we look at the composition of blood, 91% of blood is made of water. And if we remove the water, what remains are 7% proteins and other solutes. So if we consider this 7% here, this is what's really giving the plasma its yellow color. It's made of albumin. And when you think albumin, think egg white. It's got this yellow, fatty kind of a quality to it. And it's the fluid that the red blood cells are floating around in. Egg white and these other substances here are composed of what are known as long-chain fatty acids, and that's what gives it the yellowish color. And if you remove all of the water from that, it's crystalline in nature. This is what human albumin looks like when all the water is removed. So this is what albumin looks like under a microscope. Now take a look at this. Does that look familiar? How about now? How about now? So this is a crystalline structure, and it's found all over the plana. So here you got a nice combination of the red of the blood vessels with the iron rich, and then the plasma has also stuck to the outer side of the rock. Another angle of the same rock. So this is another specimen that I found. These kinds of crystals are found all over the plateau. I think this is a combination of the yellowish albumin mixed with the reddish blood, and so that's why it's got this dark brown reddish color. And here you can see the exact same thing attached to a rock. So you've got the iron-rich blood, and then you have this plasma stuck to the side, just like an egg white stuck to something. This is a beautiful crystal that I found, and it's huge. That's the back side of it. So there's a lot less of this on the plana. I think it's because people have collected the crystals because they're beautiful, and they've taken them home over the years. Perhaps they were removed for industrial purposes, but there's a ton of it up there. Okay, so rock, bone, rock, bone, or is it all bone? Okay, so I'm just going to cover one more short topic, and then I'll finish off by doing a summary of the things that we've covered. If we look at the skull, there are these connections between the bones that are known as sutures. And the tissue around the sutures is slightly different. You can see other parts of the bone have a grain. There's a layering depending on the way the bone is formed. But the sutures are a little bit different in their form and their shape. And you can see they kind of have this track going up. And I've found a section of the mountain on the top of the mountain that I believe may actually be sutures because it looks so different from the other tissue around it. I'll let you decide for yourself here, but you can see it's these small layers of rock that are vertical. This is on top. And then in a moment, I'll look to the sides of this path. And there you can see that it's a completely different structure. And this path kind of zigzags up in the way that a suture would. That's the final path to the peak. So that more or less covers the information that I wanted to cover in both the fourth and the fifth videos. I've managed to cram it into one video. From here, the next step would be to do some sort of crowdfunding for a DNA analysis. I'd like to eventually interview one of the geologists, perhaps somebody that worked on the mountain, and I'm a little nervous about that because of language and being perceived as a total nutcase, but it could be an interesting conversation. We've covered a lot of ground in these videos, looked at the overall morphology of the mountain. We've gone deep into the eye, deep into the ear, and examined the tissues of the mountain. Hope you've enjoyed it. I hope that you'd be content with the amount of evidence presented and that I would actually win a court case. There's a whole lot of coincidences that have stacked up. Some are very, very specific, and find it highly unlikely that I'm suffering from pareidolia, but that could be the case. I'll leave you with some beautiful pictures of the mountain. Until next time, hope you enjoyed the video series. Click like, subscribe, and share it with your friends. And I'll have another video coming shortly on another topic that I think you'll find interesting. I'd just like to send a big thank you to all the subscribers, and thanks again for all the wonderful comments in the comment threads. Take care.